Yeah, my name is Volker Lendecke. By now you should know me. And I'm going to go into a bit more detail about the nastiness of the SMB protocol that we have to implement and how we are doing it. And this is partly a talk about how I have tried to improve it for the cluster. It's not done yet. It's also because this is really a Linux and kernel community that I'm talking to. And I had great talks with Jeff Layton last night about how do we interoperate. And for the past few years, I've really tried to grab people from the NFS, from the kernel community, to talk about the special locking semantics that we have to do, that NFS has to do, that the in-kernel SMB server has to do, that anybody has to do, and how we can make those work seamlessly together. And so I want to just present what we have to do and then what we do in user space and maybe start some discussion about how we can put some of that stuff into the kernel. Okay, I come from Germany, started in Samba in 1994, porting Samba to the next workstation and fix some signal handling stuff. And I work mostly on the infrastructure, as Jeremy said, pthread pool, our T-event stuff, which is our asynchronous event loop using ePOL, and possibly in the future our U-ring. I'll talk a lot about TDB. Cluster Samba was partially designed by me together with Tridge and Ronny Sauerberg. My colleague Stefan Metzmacher he has Active Directory replication done as his bachelor work, so he's a smart guy. So I think we have gone over this. One of the main points that I want to make here is if you look at the NFS v4 RFCs, I mean, you have déjà vus every page you turn, really. Oh, they do delegations. Yes, we know oblocks and leases. Oh, they do share modes. Yes, we have share reservations, and so on. And we have, if you look at the ACL specification, it's very, very common. So I don't know who really copied whom, but NFS v4 is really remarkably similar to what SMB does. I guess so. So the comment was NFS v4, at least the ACLs, was an attempt to get Windows people use NFS, right? Okay, this way around. Yeah. And no, Steve is trying to do the other way around. So, I mean, going in circles here. Okay. So, SMB, everybody knows at least a bit about SMB here. I just want to point out, why do we have these nasty aspects of SMB? Because it came from single tasking DOS on the wire. I'm serious. If Microsoft is good at one thing, it's app compatibility back to the 80s. And if you imagine what a DOS box, a DOS application does, it opens a file, and by definition, it knows it's the only user of this file. And if you then start multitasking, if you then start networking, you have to maintain this illusion that word.exe, or .com at that point, is the only user of that file. So you need to implement proper locking. And if there's one mantra, NFS locking doesn't work, people don't use locking in Unix because it doesn't work on NFS. On Windows, applications depend on this. And so we have to implement this 100% correct. Another point is, if you go clustered for POSIX, if you think about what happens when you have to open a file, it's all just read operations. You look at the if you want to open a file, you look at the inode, you maybe look at the permissions, you might have to have had a path traversal, but it's all just read. You don't have to tell anybody, you don't have to ask anybody else live. And this is different from SMB. This is different to SMB. Because what we have is per open, we have to maintain a full file log, essentially. So by default in DOS, and that protocol element still exists and gives us great troubles, If you open a file, you can deny anybody else from open the file concurrently. And as I said, Windows depends on this. Has anybody ever seen the Excel message, hey, somebody else is using this file, do you want to open it read-only? That's share modes at work. Okay, Samba architecture. We are a multi-process architecture. We have one process per TCP connection. And if you look at the specification of the document, of the protocols, they suggest a lot of tables, like open file table, open client table, lease table, whatever, name it. And if you want to implement it the way we do it, you can't really use these tables as is. You can't just declare shared structures. You have to marshal them. You have to put them into a trivial database, which is essentially a shared memory key value store. Very, very fast. Hand-tuned for 15 years now. And yeah, it's really a local shared memory structure key value that for our purposes is really, really good and fast. What it does, so we have different clients coming in. They end up on different processes, but they have to communicate over these share modes, over leases. I will talk about those. And because there are interdependencies between the open handles, we need to properly separate, or because we really can't talk to the other processes' data structures, we have to have a protocol between those. And this initially enabled our clustering, because it's not so much of a difference if you talk to a different process on the same system than if you talk to a different process on another system, because it's all data streams. If you talk Unix domain sockets or TCP, it doesn't really make a difference from an API perspective. It's slower, of course, but TCP gives you most of what a Unix domain socket would do. Okay, what's share modes? NFS has these share reservations. It's essentially flog or whatever, whole file range, whole file logs, with a little twist. In NFS, you have read and write logs. We also have delete, which means I can open a file in a mode that prevents anybody else in the system to remove it. And if we talk NFS, if we talk kernel, this might, Jeff said that this is going to be one of the hard parts to get into the kernel. So what I want is I want to open a file, I want to set a share mode on the file, preventing anybody from deleting. Because if I give this guarantee to my client, then if an NFS client or a local process comes in and removes the file, the guarantee that I have had to give out to the client is violated. And so this is what we have. This is what we have to implement. This is what's out there. You might say, okay, we can't give this guarantee in POSIX, so we just violate those guarantees, but this is what we do right now. So we have been living with this for 25 years. But if you want to go better, if you want to improve, that's one of the discussion points that we definitely need to talk about. Okay, next thing we have, and this is what we talked about yesterday night, not over a beer because there was no beer, is leases. So SMB has proper caching, cache coherency protocol, which is I can open a file, server gives me the guarantee that I'm alone on that file, which is an exclusive lease. This means that whenever I write to that file, this can be asynchronous because nobody else cares. And the cache coherency part comes in when somebody else also wants to open this file. I am told that I have to give up my caches, and that's this whole lease and delegation stuff. That's per file granularity. If you look at these cluster file systems, they might go even sub-file or block level cache coherency protocols, talk to Ceph, Gluster, GPFS. We have per file granularity. And one of the points here is the fcontrol setlease call in the kernel. They were roughly designed after the op logs. So all this cache coherency has undergone revisions. The SMB1, as of like 20 years ago, had these op logs. And Microsoft found out that when they turned SMB2, they took the chance to really improve all this cache coherency thing to be more scalable, to be upgradable, downgradable, and so on, to become better. So they invented the leases, and the kernel API that Linux provides just does not match leases. It doesn't really match op logs either, but it's close, but it doesn't really match leases at all anymore. So we need to talk here. The next thing is, it is also important to have interoperability because of the upcoming in-kernel SMB server, because, I mean, they need to interoperate with this as well. They need to talk to the NFS server and have their share modes, leases, whatever, interoperate with NFS. So there will be interfaces, at least in the kernel, and we need to find ways to expose this to user space for us to also use. Okay, how do we implement this? As I said, our trivial database, TDB, is a key value store. And what we do is we have our central locking.tdb. And what we store there is, first, metadata. Timestamps, for example, interesting one, because the timestamp semantics that SMB requires are different from the Unix timestamps. And I could go into detail over this. What we then have is what we call share mode entry. Client comes in, opens a file, and every open handle, which roughly corresponds to a file descriptor, creates one of these share mode entries in our locking.tdb. So if you open a file 100 times, you will have 100 of those entries. And we also put in there these lease things, which is a server-side representation of the cache coherency guarantees that we have given to the client. And if you look at Samba 4.9, all this stuff is in one big record with 3 arrays, marshaled with our general RPC infrastructure, which is slow. And if you now imagine that these data structures on every open need to be completely read, on every close need to be completely read and rewritten, this is a really major performance bottleneck. Because they can really become like half a megabyte or a megabyte. And if you just have to shuffle them around in cluster just for each open, this really kills your performance. And how do you open a file now? Somebody comes in and asks for, hey, I want a file open that allows or denies anybody else from reading, writing, deleting. And so I open a file, I forbid anybody else to write to that file while I have this open. I put this entry into the file, into the locking.tdb, so a second opener comes in, reads my entry, and sees, do I conflict or not? And the way we have implemented this in 4.9 is we walk the whole entry, the whole array every time we open the file. And yeah, it was easy, but it was slow. Fun? Fun? Okay, yeah. And same for leases. Somebody comes in, wants to open a file, somebody else has an exclusive lease, and we need to break this lease. We need to tell the client, hey, please, please flush your caches that you have maintained, and please acknowledge that you now don't cache any stuff anymore, lease breaks. And we always walk these arrays, and yeah, so that was slow. And as Jeremy said, the typical case is the share root of the root directory of a share. If you have 50,000 clients, they will open a handle of this. And you will have 50,000 of these bouncing around in a cluster. Not good. Okay, TDB, shared memory, key value store, local, pthread mutexes, very fast, very efficient. but it's a data boundary between processes. Cluster TDB now extends this to a cluster. And this is the architecture. So how does it work? We have our SMBDs on different nodes accessing all the same records here. Conceptually, that's one database, although in fact it's two files on two different nodes, purely local. And if you look at this here, SMBDs, even in the cluster case, still mmap the local logging.tdb. So does ctdb, which is our clustered database, clustered trivial database daemon, which is nothing more than just a transport for our records. So what happens? SMBD opens a file, wants to create a record here in this logging.tdb. First, it needs to create this cluster wide. And what we have is a so-called L master, location master. Per record, we have one daemon that is, by hashing the key of the record, we determine, hey, 0, 1, 2, 3 is the location master for this record. We ask that guy, does the record exist? And if so, okay, we create a record where the location master is here. What happens is we look local, record doesn't exist. We ask this guy, we want record foo. This guy here now figures out foo, location master, is here, asks this one. This guy looks here, oh, doesn't exist at all. Creates one and gives us a copy of it. What this means is that these guys are just responsible for creating local records and shuffling them around. We open a file. Eventually, via services of ctdb, we get the local copy, the local dmaster copy, data master of the record, and we store our open file handle. Now, SMBD comes here, wants to also open the same file, one needs this record here. Sees record exists, but I'm not the local dmaster. I go here, this guy knows who the dmaster is, it maintains a copy of it, or it maintains information, goes here, fetches the record. And this SMBD now stores its information on top of that open file handle. So, let's go back. So, what you might have gotten is a lot of data shuffling going around. The idea of ctdb is it can be lossy. So we only ever have one recent, one up-to-date copy. What happens if if one node dies? All the copies, all the records on node A that holds open information is gone. But this is not a problem. But if you look at the data patterns that we store into logging.tdb is information about open file handles. Node dies, those file handles are closed by definition. And that is the main trick why ctdb is so fast. And once this guy here, this SMBD, has a local copy of its record that it needs to work with, it's just as if it was just a non-cluster TDB. ctdb, the cluster manager, is not involved. It can do its local modifications because all we store is ephemeral information. If this node goes away, nobody cares. We still have our old copies of the data on the other nodes, and we have a recovery process to always find the latest ones after a node has died. Going back to the share modes now. Oh no, not this one. This one here. Look here. We have one big record of all the open information in the login.tdb record. Whenever we open a file, we need to retrieve that stuff over the TCP connection that ctdb maintains. This is slow. This is a problem. And the work we are doing now is so what information do we have in the login.tdb? We have an array of open file handles. Each of these array entries maintains information about this open handle gives permission to concurrently write to the file. This open handle gives permission to concurrently read from the file, and so on. This open handle right now opens for read. So if we have an open for read entry in that array, a subsequent opener denying read will get denied because there is already an open read. And what we are doing now and what we have in 4.12 is we are not walking this whole array anymore. So we have an array of 10,000 entries with different share mode combinations, but there is one summary record now, which means when a new opener comes in, the only question regarding share modes is there anybody in this 10,000 entry array that would conflict? And what we are doing now is whenever we change this array, we update the record. We update the central super share mode, call it whatever, the summary flag. And so we are maintaining this array, 10,000 entries, all allow read. We say, okay, read is allowed in all of them. There is nobody denying read. And if somebody then comes in who wants to read, all the information that is required is to look at one flag, one bit. Hey, there is nobody in this array denying read, so I can go on. And what we are doing is we are doing lazy updates. So imagine that you create a file handle that is more restrictive than what was there. We have to do the update in the summary, just to maintain the property that the summary record has the most restrictive set of share modes, in whatever that sense. When we close that file, we cannot know, we don't want to walk the whole array, we cannot know if anybody else has been entered in the meantime more restrictive. So we can't just update the summary record. What we do instead is we don't update when we close a file. And somebody now comes in, sees, okay, I have a conflict. I would conflict. And at that point, I need to know the truth. So I open a file, I see, I want to open for read, and somebody in this 10,000 entry array denies read. And that's reflected in the summary. And in the conflict case, I have to walk the whole thing because this guy might have gone in the meantime. And so this is what I call lazy update. And if you do the statistics, or if you do the benchmarks, and in the last talks where I had 45 minutes and not only 30, I did the demos, and I got roughly a factor of 100 if you have a file with a 5,000 openers, and this really boosts up. Why am I doing this? We will do this clustered, because if you have this concept of a summary record, it's easy to extend this so that you have a summary record per node. And if you have that concept, you can really go and only look at your local stuff. The summary record per node will maintain the information, hey, even on the other nodes, there is nobody more restrictive than what we have here. So we don't have to talk to the others when we add or remove stuff. In the conflict case, of course, you have to ask everybody else, but we are optimizing for the good case here, which is typical if 15,000 clients open the share root. Nobody conflicts. Okay, next steps. Data structure optimizations. One thing that we need to do is, our TDB database is not a pure key value store like Redis or whatever any of these modern ones is. It's a key value store that has per record logs. So we can log a record, and this is required because this is needed because when creating a file or removing a file, we need to do multiple syscalls, and we need to do those atomically. And I'm almost done. We need to do those atomically. So while doing these multiple syscalls, like create the file, set an equal, set attributes, whatever, set the file length initially, and so on, allocate some space, nobody else can come in between, just to maintain the illusion that we are an NTFS file system. To do this, we hold a record log. This is a problem because in ctdb in the background also messes with our databases. And if we hold a record log, ctdb cannot do its maintenance properly. And if we are sitting in a syscall, and I told you about that some GPFS syscalls can take really long if they have to go out to the TSM to tape. While we are holding a record, we are holding a record log while TSM is busy fetching tapes from a library. Not a good idea if you want to recover at that point. If somebody is holding a log. We are moving this into a user space logging library so that it's only this particular file or not the whole cluster that is affected by somebody sitting in unlink retrieving a whole tape. That's the next step. And as I said, we need to spread this across nodes and have really local semantics so that whenever we open a file, we don't have to talk to the other nodes. And that's the ultimate goal. And when we are there, we can implement SMB semantics in a really scalable fashion. Okay. Any questions? Main takeaway, all this stuff we need to talk with the Linux kernel in a proper way. And we have our problems to do this. We have our solutions to get this moderately scalable now and much more scalable in the future. But this needs interop with the NFS people and the kernel guys. And so this was to tell you what we are doing and where we might cooperate. And now to the file system of, another project that is really, really old.